take the digital compensator challenge. Model a plant and build an optimized high-performance compensator that eliminates overshoot in less than 15 seconds. Ready, set, go. Stop. 14.65, we did it. Now let's go through the steps again, this time a bit slower, and starting with a baseline system for comparison. I use two tools for building compensators and modeling systems: a compensator designer and a spreadsheet. The compensator designer is used to model plants using characterization data collected in system, and then create optimized compensators that typically eliminate overshoot and oscillation. We can specify a desired profile, such as exponential, linear, smooth step, or smoother step, at the plant input or the plant output. In this example, we are specifying an exponential plant output. The spreadsheet is used to model the total system. The plant model is combined with the compensator and installed in a feedback loop. The spreadsheet allows us to probe internal points within the system to reveal detailed information about what is happening inside the system. SP is the set point. CN is the compensator input and error input. Cout is the compensator output. PN is the plant input and integrator output. I sometimes refer to this as the throttle setting. And Pout is the plant output. I typically use plots that are normalized in the range of 0 to 1. This makes it easier to see % of overshoot. In this example, we're going to use a plant from a digital power seminar I attended several years ago. In that seminar, the plant was given and the compensator was proposed. Using MATLAB, the seminar plant and compensator was converted into discrete time form, and this becomes our baseline for comparison. Let's install the seminar compensator and plant in a feedback loop and see what happens with a step input. The system is partitioned into a normalized compensator, an integrator, and a plant. Here's the compensator, here's the integrator, and here's the plant. It is common to combine the compensator and integrator into one block, but is separated here to show additional detail in the simulation. By normalized compensator, I mean that the leading coefficient is 1. We will change the global gain in the simulation to see the effect on the step response. Starting with a gain of 1, there are oscillations at the beginning of the step. And here you see the oscillations. This is objectionable. Let's try 0.50. Now we have a little wiggle and a small overshoot of about 2%. Here's the wiggle, and the overshoot is almost 2%, and you can see it here on the plot. This is not bad, but we've been ignoring what's been happening at the plant throttle setting, Pn. That's right here. Let's take a look at that, and we can see that the throttle setting goes negative, which is not allowed for this design. Let's try 0.40. 0.30, 0.2. Pn is still negative. It's about 2% negative, and you can see this little spike below 0 right here. Since I already know the answer, I'll drop it in now so we can see how it all ends up. Finally, we have a positive throttle. This is above 0, and this is above 0. Scrolling down, we can see the system reaches 90% of final value in 48 steps. Okay, we have a baseline for comparison. Now let's go through the steps of system identification, plant modeling, and building a compensator. In real systems, the plant may be difficult to model. The approach is to put the physical plant in a very simple closed loop with a single coefficient compensator and an integrator to remove steady-state error. This is all done in system using the actual processor, electronics, and other components that would make up the final embodiment of the complete system. We choose the single proportional gain coefficient to be very small, say 1 or 2% of the error input, so that the loop regulates with a little overshoot and oscillation. We start with the set point in some modest value, say 10% of the input range. Then we abruptly step the set point to a new value and collect data while the system settles on and regulates to the new set point. This data set includes all effects: the PWM timer system, the power electronics, the ADC converters, and system noise. Since we are measuring data in system, all effects, known or unknown, in the real physical system are captured. If it's in there, we are measuring it. Let's go ahead and get started. Since this example is using an analytical plant model instead of a real physical model, we will need to generate a plant step response dataset from the analytical plant model. Here we've put together a simple compensator that uses proportional gain of 1.5% of the error input with an integrator and a plant model. Here you see it's 1.5% right there, and here's the integrator, and here's the plant model here. Initially, the system is regulating at a set point of 0.10. You can see that here. Then is abruptly stepped to the set point 1.00 right here. Data is collected in system and then formatted into a CSV file. As we can see, there is some overshoot and oscillation, and the system eventually settles to the commanded set point. There's the oscillation, and it settles right here. Here is the generated data. COEF is the set of compensator coefficients used to collect the data set, and FS is the sampling frequency. In real physical systems, this data would be collected in the ISR. A typical control flow might be: take the ADC complete interrupt, read the ADC conversion, compute the error term, run the compensator, and output the next command to the plant. This dataset reflects this notion, that is, it takes non-zero finite time for the plant to respond to a command. In this example, the set point abruptly changes from 0.10 to 1.00. The plant had been in regulation at 0.10, so now the instantaneous error is 0.90. The compensator is computed, and the new plant command is issued. The plant response to the command issued in this time slot is measured after 1 unit of time, which is why the data appears to be skewed by 1 time slot. This is representative of how real data would be collected in a real system. Now that we have characterization data that was collected in system, let's read the plant data CSV file now. The plant model degree of complexity is increased until a suitable model is achieved using the least amount of complexity necessary to have a good model. So let's do that now. As we increase the degree to 5, we see that the plant gain is 11.1390, which is what we already know it should be, and it does not change with increasing degree of complexity, so we stop at degree 5. Let's design the compensator. We are specifying exponential output 90% in 8 steps. Exponential output 90%, 8 steps. We start with adding numerator coefficients until we are satisfied, basically no wiggles or oscillations. That looks good. Now we add one denominator coefficient and attempt to take back numerator coefficients to minimize the total number of coefficients in the compensator. That's about as good as it gets. We're going to stop at 3 and 1. That's 3 numerator coefficients and 1 denominator coefficient. Now let's see how fast we can go. At 4 steps, we see a violation of the plant input minimum, so 5 steps is the limit. Also note that we are getting an overshoot warning, but it is less than 1 part in 10,000, so let's just ignore that. At this point we have a usable solution. 3 numerator coefficients and 1 denominator coefficient achieving 90% of final output in 5 steps, compared to 90% in 48 steps for the seminar compensator. This is nearly a factor of 10 improvement in speed. Also note that the solution requires no in-system tuning or adjustment. We are done. We can copy-paste coefficients directly from the data window. There is one more thing I want to point out before we leave this screen. Notice what happens when we eliminate the denominator coefficient. There is a disturbance that shows up here. When we add the coefficient back in, the disturbance is gone and the open loop frequency response cleans up a little bit. Now if we slow things down a bit, the disturbance becomes much less of an issue. At 90% in 48 steps, 3 coefficients actually looks pretty good. In fact, everything looks pretty good. Here's 2 coefficients, and here's 1 coefficient. But an optimized compensator allows us to go much faster. Let's put it back to 5 steps and watch the data window. Let's add one more numerator coefficient. The new coefficient only makes a very small numerical contribution to the compensator output. Said another way, we're not getting anything in return for the extra work. With 12-bit ADCs, you won't even see it. Remember that the more coefficients there are, the more the processor has to work at runtime. Let's add one more denominator coefficient. Again, the new coefficient only makes a very small numerical contribution to the compensator output. So we're satisfied with our choice of 3 and 1. Back to the spreadsheet, I've already installed the new compensator coefficients in a feedback loop. For comparison, we can see both compensators in the same chart. This concludes today's video. Thanks for watching.